Hello, everyone. I'm Mike Botta, contributing editor for Pharmaceutical Processing, and I would like to welcome you to today's webinar brought to you by Particle Measuring Systems. Today's presentation is called Understanding ISO 21501-4 Particle Counter Calibration. ISO 21501-4 has two main goals: to improve instrument-to-instrument data correlation and count accuracy, and to enhance compliance with ISO 14644. By the end of this webinar, you should have a good understanding of the following concepts and how they affect your cleanroom particle counting efforts: how to be compliant with the most recent calibration requirements, sampling flow rate, counting efficiency, particle counter resolution, pulse height analyzer, false count rate, particle size setting, coincidence loss at maximum particle concentration, and maximum particle number concentration. While you are listening to the live presentation today, I encourage you to submit questions at any time by typing into the designated comment section on your screen. Following the presentation, we will have a Q&A segment where our speaker will answer individual questions submitted by members of the audience. Remember that today's webinar also will be available on demand, so you can view it again at your convenience or share it with friends and colleagues. You will receive an email with a link to access the webinar within the next few days. Now I would like to welcome today's speaker. Daniele Pandolfi is the Life Science Division Global Product Line Manager for Particle Measuring Systems. Mr. Pandolfi has had experience in particle counter instrumentation and cleanroom contamination control for more than 10 years. While building strong customer relationships, he has helped many people solve their current good manufacturing practice issues. Mr. Pandolfi has been responsible for the EMEA service department for the last 4 years and recently moved into the Global Life Science Organization. Outside of work, he's a semi-professional photographer, an enthusiast of electronics, a lover of new technology, and a keen traveler. I will now turn the discussion over to Daniele Pandolfi, and I'll be circling back at the conclusion of his remarks to begin the Q&A period. Daniele?
Thank you, Mike. Thank you for your kind introduction, and welcome everyone to today's webinar. So, as Mike's already explained, the topic of the day is understanding the ISO 21501-4 standard, which is specifically referring to the light scattering aerosol particle counter calibration. The goal of today is not to make you an expert about how to calibrate a particle counter, but of course, my goal is to give you as much information as possible to be able to read the concept you get from your supplier and be able to understand how your particle counter is performing. The agenda of the today's webinar includes, first of all, a brief discussion about the ISO 14644, and I will explain you shortly what's the reason why I want to mention this standard as well. Then we will go through the purpose and requirement of the ISO 21501, and of course, we need to touch as well the particle counter terminology and how a particle counter works, at least in theory. So why the ISO 14644 is extremely important, even relating to this topic. As you may know, this is probably the most used standard in the pharmaceutical and electronic controlled environment. It provides specific requirements for monitoring and classifying the clean room, and is also a kind of it also provides a kind of approval of particle counter as a tool, as a device for controlling your particle contamination. The reason why I want to mention this standard is because in the recent release, in the recent update of this standard in 2015, the ISO commit emphasized the needs and the requirements of the particle counter calibration. Specifically, in these slides, we can see the difference. If you compare the 1999 version of the standard with the 2015 version, you can immediately see that the instrument calibration requirement has been slightly but consistently changed. So in the past, the ISO were simply required that your particle counter must be calibrated according to the current accepted practice, but without specifying any specific standard. While in the new ISO 14644, the ISO commit include the requirement of calibrating your particle counter according with the 21501-4. Now, there is also a little note just at the bottom of this requirement, which essentially allowed you to still use some old particle counter, simply particle counter that were manufactured before 2008, which is the year when the ISO 21501-4 was released. What's the reason of this note? If you're curious and you read about the FDs of the ISO, you can find several country notes that essentially support these notes to be there. And to make the story shorter, one of the reasons was simply to allow the particle counter user to have enough time to replace their existing fleet. So it's really important for you now to consider a replacement of all particle counter in case you still have in your building, and look for 21501 compliant instrumentations. So as I said in these sentences at the bottom, the use of all particle counter may be allowed, but is of course not preferred. So make sure you will align your instrumentation as soon as possible. If you want some additional information about the ISO 14644-1 and as well the -2 standard change, you may navigate to the pmetering.com website, where we have a dedicated page about the ISO standard, the recent changes, and you can find even a couple of webinar recordings that I will be glad if you can take the opportunity to watch it. Keep going on the session agenda. Let's have a look at the main proposal requirement of the ISO 21501. So, this sentence is written in the first page of the standard, and in my opinion, clearly explain what's the intention of the ISO commit when they develop this standard. The purpose is to provide a calibration procedure and verification method for particle counter as to minimize the inaccuracy in measurement result by the counter, as well as the different in results by different instruments. So the goal of this standard is really to harmonize the calibration procedure, the calibration methodology, the standard used to adjust your instrument counting performance to a unique and universal, let's say, method. So in this way, any particle counter you will get, doesn't matter if it's from a manufacturer or another, it should perform exactly in the same way of the others, because now all of us are following a common standard to calibrate the particle counter, despite in the past any manufacturer were allowed to use any kind of different methodology for the calibration. Just the side information, the standard is composed by different chapters. We will focus today our discussion on the chapter number 4, which is related to the light scattering airborne particle counter. There's other chapter like the -3, which is referring to the light extinction, which for your information are particle counter used for pharmaceutical liquid and fluid contamination control. Let's start with the main requirement of the calibration standard. And the reason why I want to list them is to make sure you will look for this anytime you will read your calibration certificate. So make sure everything I'm listing here is reported by your calibration service center. First, the sampling flow rate. The accepted tolerance for the sampling flow rate is 5% for any instrument which has a built-in flow controller. Any instrument that doesn't employ an internal blower and a flow controller doesn't need to respect this tolerance, and in that specific case is the manufacturer that needs to provide you the specific tolerance range. Counting efficiency. This is probably one of the most important factors to look for when you read the calibration cert, and this gives you the information about how much your particle counter is capable of reading particle or of detecting particle, especially at the lowest size. And there are two tests that are designed for this scope. One referring to the minimum detectable size, so the smallest size you can read on a particle counter display, and using particle standard which are 1.5 or 2 times larger than the minimum detectable size. Then we can see the resolution requirement, and we will also touch shortly about the resolution. We will see shortly what the resolution is. Just for your information, the range is 15%, is the maximum allowed resolution. So lower is better in this case. The particle size error, which must be within 10% tolerance, the false count rate, or even call it zero count test. In this case, there is no range. So the ISO standard doesn't specify any specific range, but it's important that your particle counter calibration center will specify which is the performance of the instrument while running a zero count test. There are some other tests and parameters that are required by the ISO 21501, but those are normally evaluated at the design, development, and proof of concept stage, and these include the maximum particle count, particle number concentration, and coincident loss. So as you probably know, particle counter, especially the type of instrument we are talking about, are designed for clean room. So in case you use the particle counter in a very dirty area, or, for example, in your office environment, you may get an alarm related to the coincident loss error and the maximum particle concentration. Simply because if the number of particles exceed a certain number, the instrument may start losing its capability of detecting the size correctly and the number correctly. You shouldn't be, let's say, you shouldn't consider this too much, because if you're working in ISO class between 5, 6, 7, 8, all the particle counters that are actually in the market can absolutely work even in the dirtiest ISO class without any problem. Next is the sampling time. So very simple, the accuracy of the instrument to control the sampling time. And this is extremely important because you know that we need to control the particle in a specific period of time or for a specific volume. And of course, the volume is calculated as well, considering the flow rate and the time. And the response rate. The response rate is essentially the ability of an instrument to quickly jump from a very clean situation to a dirty situation. So how much your instrument is capable to switch from a clean air to a very dirty air sampling. Last but not least is the calibration interval. The ISO requires you to calibrate the instrument at least every year, every 12 months. I take the opportunity to even emphasize something else. So that generally, an instrument which results to be out of specification during the as-found control may result in cost for your organization, because you're required to check back your particle count and make sure they didn't exceed the GMP or ISO requirements. So, of course, this is a risk, and you can mitigate the risk of having a particle counter out of specification, for example, reducing the calibration time frame to 6 months. This may not be required for all the particle counter, but probably for those particle counters that are used in very critical area, in the sterile area, ISO class 5, and so on. So please, just consider these as a possible alternative, as a possible solution to mitigate the risk of having an out of specification. As I mentioned before, the standard includes other chapters. We will be focusing on the chapter 4 today, and this is actually considered the statement of laser particle counter capabilities. Twisting the meaning may result in unnecessary cost for your organization. What does it mean? I just want to make sure that you do not try to exceed the requirement of the ISO 21501, for example, by requesting your calibration lab to reduce the tolerance range from 10 to 5% or similar things. This is really not required. This is really unnecessary and may only result in additional cost for maintenance costs for your instrumentation and, of course, for your organization. Let's now have a look about the particle counter calibration terminology, but before doing that, I would like to show you how a particle counter works. So what you can see on the right side now is a drawing which represents an instrument optical cell. This little black dot represents a particle that is just flowing into the instrument optical cell. On the left side of the drawing, there is a laser diode which generates this red beam light. This particle, while flowing into the optical cell and will face the laser beam, will scatter the light all around itself. This light, while scattered, will be reflected by elliptical mirrors, and then will go all the time, because of the design of the mirrors, will always be reflected to the photodetector. The photodetector is essentially a light sensor, similar to the one that any one of us has on the smartphone. So in our smartphone, this light detector will help the smartphone to adjust the brightness of the display. So if you are outdoor, they will be increasing. In this case, inside the particle counter, this photodetector will help us to detect the particle, of course, and to understand which is the size of the specific particles. So the scattered light will become an electric signal, and so to be accurate, it will generate pulses, and these pulses will be counted. So in this next slide, I want to show you what happened behind the scene. This is, of course, something you don't see from your particle counter. You will see number on a display, but what happened behind the scene is essentially represented in this graph. So there will be pulses, one per each particle, and as you can see, each pulse may be different from the other, and the difference is based on the size of the particles. So a little particle like a 0.5 micron will result in a small peak, while a big particle, in this case a 5 micron particle, will result in a higher peak. So by using what we call threshold, and they are represented by these dashed lines on the screen, our particle counter is able to understand if the particle that just flowed into the optical cell was a small particle, a big particle, or a 1 micron, a 2 micron, a 5 micron particles. Every time you send your particle counter for calibration, the engineers in charge of calibrating your instrument and adjust your instrument performance will essentially adjust and move up or down this dashed line. These are this threshold can be considered by yourself like a set point. Let's call it set point. So here's the explanation about each single test. The first test that is always performed on your particle counter is the flow rate calibration. The flow rate is extremely important because first, it must be accurate because the instruments are normally designed to work at the specific flow, and also because the flow rate is directly affecting the volume that is sampled by your instrument. Why the volume is important? Because you always refer your particle count number to a volume of air. If you look at the GMP Annex 1 table or the ISO 14644-1 table, you will always see the maximum permitted particle number in a volume of air, which is normally 1 cubic meter. So you can easily understand that an accuracy in the volume sampling is extremely important. As I said, the passing range for instruments that are employing a flow controller is 5%, while the instrument without a flow control system doesn't have a specific passing range, and is the manufacturer that is allowed to define the specific range. So ask your supplier to provide this information. Still talking about the flow rate calibration and the flow rate detection, it's important that the instrument you're using will be able to detect the volumetric flow and not only the mass flow. Why this is important? The volumetric flow is affected by different things. First of all, it's affected by the atmospheric pressure as well as the temperature. So to be able to accurately detect your volume, the instrument should employ additional sensor inside, for example, an atmospheric sensor and the temperature pressure, which in real time will be able to fine adjust the sampling flow rate speed, and so the speed of your blower. So just to give you an idea, barometric pressure can induce error as large as 3%, and barometric pressure can change based on altitude. So if you're located on a sea level or are located up to a mountain, of course the barometric pressure may change, but also a rainy day will have a different pressure, atmospheric pressure, than a sunny days. So having an instrument which has like in our case, a patented system to detect the volumetric flow will mitigate the risk of detecting the volume in a wrong way and induce error in the volume sampling. Let's jump to the false count rate, or even call it the zero count test, or even call it the measure of noise. This is really a measurement of noise, simply because any electrical system, any electronic board has a certain amount of noise generated by the power supply and electronic stuff that I will not bother you describing right now. But what is important to understand is that anytime you send your particle counter out for calibration, your size threshold will be adjusted. And time by time, it may occur that your size threshold dashed line, like in this case, may be adjusted close to the noise level. The result of this will simply be that your instrument will count false particle, will count the noise, because these little peaks that you can see on the screen, which are representing the noise, may be simply misunderstood by the instrument like real particles. So, as part of our calibration test, we always test the zero count or the noise level at the end of any calibration to make sure that our calibration didn't went close to the noise level. And as well, this test can help you understand if the particle counter optical cell is clean. is not contaminated, and is not introducing particles to your analysis. This is a very simple test that you can do by yourself, and I personally recommend you to do even every day before starting your operation or on a weekly basis. It just requires you to use an HEPA filter, most of the time designed for the specific particle counter, plug it in, run a 5-minute sample, and make sure your instrument is not counting particles. Doesn't necessarily need to be an absolute zero, but maybe just a 1 or 2 or 3 particles are accepted. With this test, you can quickly understand if you are getting the risk of overcounting your clean room contamination level. Here on this slide, something I personally think is interesting. So these are images about real particles under a microscope. So why I'm mentioning that? Because what we use to calibrate the particle counter and what the ISO allowed as a standard for calibrating the particle counter are not exactly the same of how the real particle looks like. So real particle may have a lot of different characteristics like the length, the weight, the volume, the color, of course, the orientation. The material may be different, of course. What we use is what is called an optical equivalent. So these are polyester and latex sphere. And I'm pleased to show you an image about how they look like. So here in this slide, on the right side, you can see bottle containing particle standard, even called PSL particle. And here in this little image, you can see 4 little 5-micron particles on a cotton fiber. This is an image taken under a microscope that shows you how the particle we use to calibrate your instrument looks like. So the ISO allowed to use this kind of standard, and so they are accepted as a substitute for real particles. They are round, they don't have any orientation issue, and of course they must stay into a specific range, specific tolerance range dictated by the ISO 21501. The counting efficiency. Also the ISO 14644 talk about the counting efficiency, and this is the ratio of reported UUT count to a reference. UUT means unit under test. This is essentially your particle counter, the one that you send to the calibration lab to be calibrated and adjusted. To test the counting efficiency, the unit under test is challenged with a certain amount of particle, and the results are compared with a reference unit. A reference unit is, let's say, the gold unit that is used to verify your instrument performance. Of course, this reference unit is as well calibrated, but the calibration of this reference unit employ some different system, we may say a little bit more complex and complicated. And just to give you some information, the Scanning Mobility Particle Sizer, SMPS spectrometer, is used together with the CPC particle counter, condensation particle counter. They are shown here on this image. On the right side, you can see the SMPS, which employ a radioactive source and essentially give us the ability to generate specific particle size. So we can tell this instrument, I want the 0.5000 micron particles. It's able to generate that, and then this little box on the left side count this particle with a very high efficiency, and again, this is considered actually the gold standard for particle counting. The number obtained by this system are compared with the reference unit that we calibrate at the higher frequency of your unit under test. And this instrument on the front is actually our Laser 2110, which is our reference unit, the one we use for calibrating your particle counter. Another important test we perform, another adjustment we perform is the size setting. So why we adjust the size? First of all, because there are no commercial available methods to compare efficiency of counting above 1 micron. So the SMPS system that you've seen, together with the CPC particle counter that you've seen on the previous slides, they can't work above 1 micron. And so the sizing is the method we use to make sure the instrument is able to detect the right dimension of the particle. This test employed the use of a PHA, pulse height analyzer, and the standard required that at least 3 particle sizes are tested. The particle size test is performed in conjunction with the Mie curve. This calibration curve is created during the design of the specific particle counter model and allowed us to understand right quickly what is the error in size, the error in micron that the instrument is doing. So these multiple dots are representing the number of tests that has been performed on a single particle counter. So we do not only test particle size like 0.3, 0.5, and 1, but hundreds of intermediate size are tested between each single channel. So by doing this, we can compare, every time we adjust the threshold of your instrument, we can compare the previous threshold with the new threshold, and so we compare the two set points, and then we can translate these differences in micron size difference. So how your instrument was, how big was the error your instrument was making in detecting the 0.5 micron instead of 0.49 or 0.48. So the error, the accepted error is 10%, and in the next slide, you can see an example of 2 instrument resulting curve with the previous calibration threshold at 158. This is just a number. This is a number in bits, but this may be just a voltage number in volts, and the new one, which is 165. So comparing these two numbers and evaluating the difference between these two numbers with the Mie curve, we can understand what is the error the instrument is introducing in understanding the size correctly. Why this size is extremely important? I believe these slides clearly explain that. What you can see on the screen now is called a real-world distribution of particles, or power law distribution. I'm sorry, but the number on the graph are extremely small, so you can't probably read that. Anyway, if we evaluate the graph, on the right side, we have a particle size at 10 micron, while on the left side of the graph, at the bottom, we have a size around 0.2 micron or 0.3 micron. As you can see, the distribution of particles in the real world, so in our environment, is not linear from the small to the big particle, but is represented by this curve. This to say that an error in size is also an error in number of particles. So if your instrument is not detecting the right size, it's also not detecting the right number of particles. A particle measuring system, we can provide you, in a rare case, your particle counter will be out of specification at a certain size. We can provide you correction factor, which take into the account this power law distribution curve and may give you a usable tool to quickly understand the real number of particles that the instrument should be counted and maybe wasn't because of an out-of-spec situation. The next parameter that is very important is the size resolution. The size resolution is essentially the ability of the instrument to detect the right size in an accurate way. So as you can see on the right side, we have three representations of a Gaussian curve with the moderate and good and poor resolution. So what happens if the instrument has a poor resolution? Have a look at the size A and size B threshold. They are very close one to each other. So in the poor resolution case, when the instrument count and detect the pulse, the two curves are almost overlapping one to each other. This means that the instrument, in this case, will not be able to detect if the particle just counted is referring to a size A or a size B. While in a good resolution state or a moderate resolution state, you can see two different curves, and you can see that they are far one from each other, and so the accuracy in the detection of the right size is higher. So in the ideal world, you should have a straight line instead of a Gaussian curve, but due of a multitude of different factors, parameters, and inaccuracy of the standard, a straight line is essentially not possible, and you should expect your particle counter to have a narrowest possible curve. Why the resolution may be not perfect? This is almost related to the laser beam characteristic and performance. So particles that fly, just have a look at this circle, this red circle. If you look in the middle of the circle, the red color is darker, is stronger, while on the edge is becoming a little bit clearer. So if your particles fly just in front of the center of the laser beam, this will result in a higher peak. And if it fly in front of an edge of the laser beam, this may result in a smaller peak generated by the photodetector. Now, the actual technology allowed us to minimize the effect of this and also help in maximizing the performance of the laser diode by employing different lenses which increase the focus of the laser, which adjust the orientation of the laser. But just to say that one of the factors that may affect your resolution performance is, of course, the laser beam. The last concept I want to explain today is about the maximum particle concentration and coincident loss that I mentioned at the beginning of this presentation. So as I said, in case of very high concentration of particle, the instrument may lose its capability to detect the numbers and the size correctly. Why? And this drawing on the right, I believe, explain it better than what I can. So in the case, two particles just fall in front of the laser beam all together at the same time, like in this case, this may result just in a single larger particle. So in case of very high concentrated environment, this is something that may occur, and the instrument may lose its capability of correctly detect the number and the size of the particle. In case, as I said, particle counter available in the market doesn't have any problem in dealing with ISO class 8 or even dirtier area, But in case you are going to perform tests like recovery tests, which require the use of particle generator or smoke generator, make sure you do not exceed the maximum allowed concentration. And if this happens, make sure you will use an appropriate system, which are normally called a diluter, to avoid the instrument to deal with the too high concentration of particles. So we are now at the end of the presentation, and we will then go to the question and answer session. Just to recall what we discussed today, the particle counter calibration is a balance of multiple specifications defined by the ISO 21501. Unfortunately, the calibration of a particle counter is not easy, as it can be a calibration of a pressure sensor or a temperature sensor, which only imply a single parameter to be tested. The calibration must include, and this is what you should always read on a calibration certificate: the size calibration, the size resolution, counting efficiency, false count rate, and sampling volume uncertainty. The standard, as I said, is essentially a statement of particle counter capabilities, and we recommend you to keep your particle counter under calibration at least once per year, or even more, to make sure this will not result in any out of specification will not result in extra cost for your organization. I will now give back to Mike to proceed with the question and answer session.
Okay, well, thank you very much, Daniele, for that highly informative presentation. And we are now taking questions, and we already have some excellent questions that have come in, but I'd like to encourage our listeners to continue to submit your questions at any time by typing into the space provided on your screen. All questions that are not discussed in the Q&A segment will be answered by representatives of Particle Measuring Systems at a later time. So let's go to our first question here. We have a question: does ISO 21501-4 apply to compressed air and air particulates in clean rooms?
So the ISO 21501-4 doesn't specifically talk about compressed air testing. However, the instrument that you are going to use to test your compressed air must be calibrated according to 21501. I recommend to have a look at the ISO 8573-7 for additional information about the compressed gas testing, and also have a look at the pmeasuring.com website, where we have a recorded webinar and an application note which specifically talk about particle testing and microbial testing in the compressed gas.
Okay, thank you. And we have another question here. Is the particle counter calibration a must? And the word must is in quotation marks. So I turn that over to you, Daniele.
Yes, the particle counter calibration is a must. So you should think about the importance of the data you're going to obtain from a particle counter. Most of the time, you use this data to release batch of product and so on. Plus, we need to mention that the standard, the actual standard, the ISO 14644 and the ISO 21501 require you to calibrate your particle counter at least once per year. So not doing that will result in authorities, non-conformity, and of course, not nice situation with authorities.
And now we have a question: why should I look at the ISO 21501-4 as the standard for particle counter calibration?
Sorry, can you repeat the question?
Sure. The question is, why should I look at the ISO 21501-4 as the standard for particle counter calibration?
This because the recent update of the 14644 required you to look at this standard as a mandatory method for calibrating the particle counter. So it is required by the monitoring and classification standard actually used in clean room.
And I guess as a follow-up, here's a question. To your knowledge, have the EU GMP guidelines accepted the ISO 21501-4 requirements?
Yes, it does, because the EU GMP referred to the ISO 14644 in multiple parts without referring to a specific version of the ISO standard, which means that always the latest one is applied. Now, if you read the 14644, it required you to use 21501 calibrated instrument, and so as a consequence, even the GMP has to follow this requirement, and you are required to respect this requirement if you're using a GMP standard.
Okay, now we have another question here. If my equipment is not calibrated and cannot be calibrated with this standard, will it affect our particle counts?
That's an interesting question, Mike. So it's out of any doubt that the technology about the particle counter detection has improved during the last years. So if your particle counter is not compliant with this with the ISO 21501 standard, it means that most probably was produced at least 10 years ago or even more. So there are different reasons why the accuracy of the particle counter you're using may not be the same as the actual available particle counter. And so I recommend to look for something new and updated to accomplish your monitoring activities.
Okay, and here's an interesting one. What's the best way to calibrate ambient monitoring stations deployed in the field?
Ambient monitoring station that are using in the field. So the way you can, of course, you need to refer to a certified, authorized calibration center, but this particle measuring system also offer service on-site in the field for calibrating your particle counter to reduce the time necessary and to avoid you to have your instrument outside of the building for a long time.
Another question, what's the typical lifetime of a particle counter?
Interesting question. So I would say that we still have 20 years old particle counter out in the field that are even working properly. So it really depends on a lot of factors. So a typical, let's say, a typical life of the laser diode may be around 8 years, 7 years, 9 years, but mostly depend on how do you use the particle counter, the environment, the temperature of the environment, the moisture and humidity, and also the frequency of use. Of course, an instrument that works 24 hours a day is different from an instrument working 1 hour a week. So I would say that instrument normally work for 10, 12, 15 years without any problem. With, of course, annual calibration and normal maintenance and normal part replacement while they are broken. I take the opportunity to mention something else. All the PMS particle counter also employ some real-time control on the most important hardware pieces like the laser beam and the blower. So this control will allow you to be notified immediately if the blower or the laser or any other critical component is running, is performing bad or maybe need to be replaced. So don't I just suggest you don't care too much about a specific time frame, but trust what the instrument is notifying you in terms of alarm and hardware alarms.
And also on the subject of alarms, this question came in. Does this instrument monitor 24 hours, 7 days a week, and report or alarm out-of-range measurements of particles or microbes?
So if the question is if the instrument is able to provide alarm?
Yes, that's what it looks. That's what it looks to be. If it's does it monitor 24 hours a day, 7 days a week, and does it report or issue an alarm for out-of-range measurements or particles or microbes, which seems to be a bit of a follow-up, I think, to that last question.
So normally, instruments used 24 hours a day are connected to what we call facility monitoring system, which are able to provide you immediate alarm and notification by light, by sound alarm, and so on. So this is based on the configuration. Even portable instruments can be configured to provide alarm, and alarms that are triggered when you exceed a certain amount of particles.
Okay, and this question is, can we make adjustments in calibration on the particle counter, or is this locked out by the manufacturer and only the manufacturer can make those adjustments?
So normally this is locked by the manufacturer also to avoid the instrument to be adjusted by non-expert engineers and people that doesn't know exactly how to do a calibration. As I probably explained before, the calibration of a particle counter is not something really easy. It includes a lot of different tests. It requires the use of sophisticated system, and so I would say refer to authorized center, and most of the time to your manufacturer calibration service lab for calibrating your particle counter.
Okay, and this one I think you touched upon before, but the question came in, how frequently do I need to calibrate my particle counter? So that must still be a question out there.
Yeah, at least one per year. Once per year is the requirement of the standard.
Okay, and let's see here. We have are handheld particle counters compliant to this ISO?
Can you repeat the question?
Yes, it might be a little unclear here. Are handheld particle? It looks like they're asking about handheld particle counters, and are those compliant to the ISO?
So as the handheld particle counter as well needs to comply with the 21501-4 standard. Handheld particle counter are simply smaller and portables, but they do the same job of others particle counter and need to follow the same kind of standard.
Okay, and here's an interesting one. Are there any significant changes expected between ISO 21501-4 2007 and the draft ISO DIS 21501-4?
Yeah, that's the 21501-4 is actually under revision. There will be some differences that I will not address today, since because are still in a draft version and may just create some confusion. But yeah, there will be some changes, but maybe not so dramatic, let's say, no big change, let's say. There will certainly be some more emphasis of maximum permissible error, uncertainty in calculation, and this kind of methodology-related stuff.
All right, and this question just came in, and I think it's more in reference to the earlier question. So, is the issue really whether and how much you trust you can really put into a manufacturer's calibration? And I think that had to do with the earlier question about whether or not one can change the calibration or it has to be done by the manufacturer. So again, the question is, so is the issue really whether and how much trust we can really put in a manufacturer's calibration?
You should trust the manufacturer calibration. So I think that the manufacturer calibration it's something that you must trust and you should consider feasible, while third-party calibration may be accepted, but you should prove that the third-party calibration are performed using the right standard, following the right procedure, and you need to make sure that any third-party laboratory that is performing your calibration has the ability not only to calibrate your instrument, but also to adjust the counting and the sizing threshold of the instrument. This because if you use a third-party calibration lab that is only verifying your instrument, calibrating your instrument, but not adjusting, you may take a risk of having an out-of-spec situation in a year or in 2 years. So it's always important to recenter the instrument performance, the sizing calibration, every time you calibrate the instrument.
Okay, Daniele, and due to time constraints, this is going to be our final question for this section. How is the traceability of particle counter established? And so I guess that's on the question of traceability and serialization and so forth. So how is the traceability of particle counter established?
So particle counter are normally calibrated with the NIST traceable standards, and also particle measuring system offer 17025 calibration with traceable standard, and any service provider should also be able to trace the loop of measurement from the standard for all the standard used. Okay,
well, thank you very much. That concludes our webinar today, and I want to thank everyone for attending. And certainly a special thank you goes to our speaker, Daniele Pandolfi, and also to our sponsor, Particle Measuring Systems. Now, for our audience, look for an email with a link to access this webinar on demand within the next couple of days. And with that, we'll wrap up. I want to thank everyone, and I hope you all have a great day. Thank you.
Thank you, Mike, and thank you, everyone, for attending. I wish you a good day.